Speaker for this session will be David Kahn, who is going to present us a new flavor of operational semantics, halfway between big step and small step. In a minute. Time to find the slides.
Plugged in.
HDMI. Yep.
Yep.
Thank you.
Are we there? There we go. Well, hello everyone. I guess without further ado, let me tell you a little bit about big stop semantics. So this is talk is going to start with just a quick little recap of some of the classic bangers of operational semantics, and which is what everyone in this room probably knows and loves. So I'm going to start with the small step semantics. Those came on the scene around 1981 with Plotkin's structured operational semantics. And the way that small step semantics specifies the behavior of a program is by specifying the very next step that that program will take. All right. And if you want to express longer computations, all you do is you chain together a sequence of these single steps. So for a quick example, 1 plus 2 plus 3 plus 4 takes a single step to 3 plus 3 plus 4, 3 plus 7, and then 10. That's small step semantics. Now let me tell you a little bit about the other big player in operational semantics, and that would be big step semantics. And that came on the scene around 1987 with the work of Kahn, no relation. And unlike small step semantics, big step semantics works by trying to directly relate an expression to its resulting value. And the way that it does that is by breaking up an expression into meaningful chunks and reasoning about how those different chunks evaluate. So for example, the same previous expression we just looked at has these two significant sub-expressions, and they evaluate to 3 and 7, so the overall expression evaluates to 10. Great stuff. Now, big and small step semantics are usually considered to be equally good for specifying the behaviors of programs, and you might have even encountered a theorem like this in some undergraduate course that explicitly says that the expressivity of both of these kinds of specifications are equal. But there is a small caveat to this theorem that is somewhat easy to overlook, and that is that it only holds for terminating expressions. To see why, consider some E0, which is an expression with a non-terminating execution. Small step semantics can work with E0 with no issue. It can just keep stepping along as far as you would like, and as a result, it can capture all finite prefixes of this computation. This is a happy circumstance, because it is sufficient to prove invariance about the program's execution, such as, for example, type preservation. And this holds even for infinite computations as well as finite computations. It covers all kinds of programs uniformly in that way. On the other hand, big step semantics immediately gets stuck. It can only relate an expression to the value that its execution terminates with, and E0 just doesn't terminate. Thus, big step semantics simply does not define the computational behavior of programs that don't terminate. This is not a very happy circumstance, as it means big step semantics cannot be used for verifying properties of such non-terminating expressions. As a result, whenever non-termination is on the table, people often reach for small step semantics. Now, the thing is, non-termination is often on the table, or at least the ability to run a program indefinitely, if not infinitely. And this matters. For example, consider a web server for a website. When you log on to your favorite website, you would hate to find that the program on that server has just terminated and that website is inaccessible. Or perhaps more seriously, consider a medical device that needs to be able to run as long as it needs to help the patient. An airplane. If an airplane gets diverted from its path and needs to stay up in the air a little bit longer, you would hate to have that flight control program terminate its execution. And for maybe an application that's a bit more in focus in this community, if you're going to make a compiler, you just kind of have to put up with the fact that people can write infinite loops. And the thing is, while true should not set your compiler on fire. Undefined behavior just isn't good enough for fully specifying the behavior of a programming language. and just isn't good enough, therefore, for formalizing a compiler. So we can't use big step semantics for this purpose. So if we wanted to pick out an ideal operational semantics, the first item we might put on our wish list is this, that we can handle all programs, terminating or not. And we'll add to this list as we go through the talk. So sure, it's true that big step semantics is inadequate when it comes to non-termination. It just doesn't satisfy that item on our wish list. But so what? We can just use small step semantics, right? And indeed, nothing stops us, but it would be a lot nicer if we didn't. Anecdotally, and even with a lot of data to back it up, many people in this community have pointed out that big step semantics is just nicer for the proofs of many program properties. The big step rules themselves are usually more concise because they don't have to deal with all the baggage of congruence rules that small step semantics has, which can make it a little bit easier to set up a proof. And more importantly, the proofs using big step semantics tend to follow by direct rule induction over the derivation of the operational semantics. Whereas for small step semantics, the proofs are often quite indirect and can sometimes require some non-trivial invariants. So while it may not be a hard and fast rule that big step semantics leads to nicer proofs, it certainly leans that way on many of the proofs that I am interested in. And so I'll put a second item on this wish list. It would be good if we could maintain some of the niceties of big step semantics, especially with respect to proving. So rather than use small step, it might actually be worthwhile to look back at big step semantics and find a way to salvage its use for potentially non-terminating programs. And the thing is, we aren't the first to have realized that this would be worthwhile. Let me just tell you a little bit about some prior work. The vast majority of it is based on co-induction. And this started at least with Cousseau in '92, and many, many more have built upon the same basic idea since then. To give you the basic flavor of this approach, here's just one rule that might come up for function application. To co-inductively establish that an application of the expression E1 to E2 is non-terminating, that's that infinity symbol, it suffices to co-inductively establish that E1 is already non-terminating. And the derivation for E1 would need its own non-terminating premise ad infinitum. And this approach works just fine to co-inductively pick out non-terminating expressions, as witnessed by just how much work is built off of this approach. But just because an approach works does not necessarily mean it is the easiest to use in practice. Even if you are already comfortable using co-induction, it can be non-trivial to mix co-inductive definitions with inductive ones. And this non-triviality is also probably why many proof assistants have had issues supporting co-induction. So even if you are working in formal verification and want to use co-induction, even if you stick to the rails of your proof assistant, you sometimes need to be careful because things can go wrong. So for these reasons, it might save us some headache if we could instead pick a purely inductive system. So let's add that to our wish list. So then maybe we should look at some prior work that is inductive. And the thing is that there really hasn't been all that much. One example is what are called partial proofs. And these add two mutually recursive judgments to the semantic system. One is the redex judgments, which progress the derivation, and one is the search judgments, which don't. And these judgments range over values and as well as some special metavariables called logic variables that stand in for incomplete derivations. Another different line of work is the work that uses step counters. These step counters are used as fuel, and the way that they affect the semantics of the program is that when the fuel eventually runs out, the program will immediately terminate with an error. And this prevents running for indefinite lengths of time because you only have finite fuel. An example of such a rule in this system would be the following, again for function application. And what this says is that if you're going to run out of fuel when you're computing E1, then you're going to also run out of fuel, even if you have one more fuel, when computing the application of E1 to E2. All right, so that's just two examples. And while all of these inductive approaches do work, you'll notice that they all end up imposing some extra proof obligations to deal with all the extra things that they add to the semantics. In the case of partial proofs, you have to juggle multiple kinds of judgments and now multiple kinds of variables. And in the case of fuel, one often needs to quantify over fuel amounts and then discharge that quantifier. It is important to know, for example, that computation is sufficiently independent of the fuel amount as long as you have enough fuel. So that brings us to, I guess, the final item to add to the wish list. It would be good to have just a simple, single kind of judgment that doesn't add a whole lot of new pieces to deal with in the semantics. Ideally, we want something minimally invasive that is almost just the big step semantics, so that our proofs remain just as easy. Now, there is actually one other piece of prior work that I haven't mentioned yet, and that is the partial big step semantics of Hoffmann and Hoffmann. So this work can capture non-terminating programs inductively in a big step style, which is almost everything on our wish list. But like the other inductive work we saw, it isn't quite all that simple. You see, this work is specialized for giving the cost semantics of a functional programming language. And to do this, it actually augments its judgments with quite a few things, counters as well as heap and stack. But unlike other work, these augmentations don't actually play a big role in how the system reasons about non-terminating computations. Instead, what this approach does is it adds a whole new specialized judgment to represent a partially complete evaluation. And then the semantics allows non-deterministic halting with this new judgment, so that a program can sort of stop at any point and recount the cost it has accumulated so far. And I had actually been working with this system for quite a bit in some of my other work, when I eventually realized there was quite a lot of room for taking this non-deterministic halting idea a bit farther. In particular, it might be possible to get the same result more generally and more simply, getting every item on the wish list. And somehow it doesn't seem to have been done before. That leads us to big stop semantics, because it maintains the core idea of partial big step semantics, which is the ability to non-deterministically halt or stop. And this is going to give us everything that we want on our wish list. So let me start by showing you an example of how simple it is to turn some big step semantics into big stop. And I'll do that here for a simple PCF-based language as displayed. These are the big step rules, but I don't want you to care too much about any of their details. I just want you to see that here on the top, we have some of the basic computational regex rules. We have recursive function application. We can case on natural numbers. And then on the bottom, we have the remaining rules, which are basically values and congruences on values. To make this big step system into big stop, all we need to do is make the following change to the rules. Boop. And this is one singular new rule schema, and it captures what it means now to non-deterministically stop. Let me show you exactly how it does this by instancing it on the stopping rules for function application. So there are three ways that function application can stop. First, it can just immediately stop, and that will leave the left and right side of the judgment the same. And in fact, the stopping rule is set up so that every expression can big stop to itself, which is why we no longer need a separate rule for stopping values. The second instantiation is that we can begin to partially evaluate the first sub-expression, here the function E1. And you can see how that partial evaluation E1 prime takes the place of E1 on the right. This kind of behavior is why we no longer need separate congruence rules. And finally, we have the ability to partially evaluate the second sub-expression, but only after fully evaluating the first. This ensures that we maintain the order of operations that the language demands. So these are the ways that an application can non-deterministically halt, but do note that an application could also just evaluate as normal. It's all non-deterministic. The key reason why this non-deterministic stopping actually works can be seen by recalling small step semantics for a moment. In particular, how small step semantics handles infinite computations. Small step semantics lets us increment our computation one step at a time, allowing us to stop between any two steps if we so wish. And at that point, we can inspect the partially evaluated expressions that we find. Considering all the places we can stop gives us a very easy form of theorem statement. If we can stop at some intermediate point, then x holds there, where x is just whatever property we're interested in, like type preservation. And this shows that x holds as an invariant across all of computation, infinite or otherwise. So what does big stop semantics do? Well, the same thing. It just uses deeper and deeper derivations instead of taking more and more steps. And so big stop allows the same convenient form of theorem as small step. Just now, instead of having to work with cumbersome small step relations, we can capture all the same stopping points with a convenient big step style relation. And the equivalence in stopping behavior between small step and big step can be made precise with the following. If you can big stop to some expression e prime, then you can reach that same expression e prime with small step, and vice versa. And for good measure, we proved this theorem in ACTA. So now you might be wondering, so what? Doesn't this just show that you don't gain anything over small step? Well, the answer is that this equivalence shows that big stop can get the same theorems as small step, but now we can do so with easier proofs. And we actually backed this up a little bit with a case study. So what we did is we considered compiling our PCF language by tossing it into a Kriven machine, or K-machine for short. A K-machine is just a stack-based model of computation, kind of like the Zinc abstract machine, which underlies OCaml's bytecode interpreter. So this simple compilation actually has some real-world parallels, and we would like to verify that it is correct. Formally, that means that our PCF semantics describe some program behavior if and only if the K-machine describes the same behavior. And just to make things interesting, let's add in effects as well. That makes it all a little bit more real-world, and also means that non-terminating computations can have observable differences, because we can look at the effects rather than just the resulting value. So here we have the terminating cases for proving that theorem. The first case for terminating programs is terminating soundness, saying that if the K-machine can show some behavior of the program, so do the big stop semantics. And then secondly, we have terminating completeness, which shows the reverse. And terminating completeness is actually the interesting one to look at, because its antecedent is the semantic relation. And so this is where we might induct over the derivation of the semantics. If we were using small step semantics instead of big stop, this theorem would actually pose a bit of a problem. See, the problem is that small step semantics forms chains like this, where the resulting expression E1 is also the input expression to another relation. And so in order to apply the inductive hypothesis, we need to search for a K-machine state that can properly correspond to E1. The problem is that K-machine state simply may not come up. There's not a good correspondence between the small step semantics and the K-machine. And so instead, the textbook approach to proving this is actually to just use big step. Turn small step semantics into big step first, and the proof proceeds by simple induction on the derivation. So that's all fine with the terminating cases. But what about the non-terminating cases of correctness? Well, we again have some non-terminating notion of soundness, which says that if we can partially evaluate an expression inducing some effects, then we can do so with either the K-machine or our big stop semantics. They'll do the same thing. And non-terminating completeness will give us the reverse. And so again, completeness is the case that's worth looking at, because its antecedent is the big stop semantics. But this time, neither small nor big step semantics is sufficient. Small step semantics has the same problem as before, but big step semantics can't formalize partial computations. So we would be stuck if not for big stop semantics. And so to finish off this correctness proof, we use what we call the big stop method. We start with the standard big step theorem. We extend its rules of the big step semantics into big stop. That gives us a very trivial terminating theorem, because we already had the big step theorem. And we just need to add new proof cases for the stopping rules. The result of doing this formalization of the correctness, specifically for completeness, looks like the following. And I could talk about all these numbers quite a lot, but I'll suffice it to say that the big stop semantics shows that we can get all the results that we want for terminating and non-terminating programs with relatively few lines of code, especially compared to small step semantics, which is often twice as big. Now, the final thing I'll say is that for big stop semantics, you'll notice that the non-terminating proof is about twice as large as the terminating one. And this is because we used that schema, which breaks down into many different rules that we now need to cover. But in the paper, we also show you can optimize big stop semantics to require just one new rule. So here's an example where all of these rules are from the original big step system, and this single simple rule here is from big stop. And this is just a single simple rule, not a rule schema. And so that's all. The paper describes this big stop system, proves its formal properties, exhibits the efficacy of it with this case study. We show how we can optimize the number of rules we have to actually create. And we also show that it works in the paper, in the extended work, for like imperative languages as well. So it's actually quite applicable. That's all I have. Thank you.
So when you're talking about corresponding big stop and small step semantics, there is kind of implied assumption there is some states which are synchronized between the both. Is that correct?
I couldn't quite make out the end of that question.
You can hear me? I can repeat. When you're talking about comparing big stop and small step semantics and correspondence theorems, is there an implication that there is some states which must be synchronized between the both?
So for the theorems that we have proved for like the K machine, we don't have any statefulness, but when we show in some of the extended work how to extend this work to, for instance, an imperative language, then we do have state. I'm not sure if that's exactly what you were asking.
Just quickly clarify. For example, you have a defined in big step operation with 3 arguments, plus and multiply, as a single thing, and in the small step it's 2 separate steps. You wouldn't be able to correspond them.
Yeah. It's a tight correspondence. They exactly represent the same relation.
We have another question on the other side.
Hello, thank you for the talk. I'm wondering if you lose inversion and if that makes any proofs harder with big stop semantics.
I'm sure that there are some proofs that end up being more difficult, but a lot of the proofs that one might be interested in, I keep thinking of type preservation, for example, tend to just follow more easily if we use a big step style approach. So while certainly there's not necessarily any best proof system, I think big step style semantics come up often enough as something that's cited as making proofs more easy for things like, for example, proving the correctness of compiler passes and such. I can't think of any good example where small step semantics is the better alternative.
And one more question before the next speaker sets up.
Thank you for the great talk. I'm curious if there was any prior work. I'm over to the left, but if there any prior work to show correctness for compiling to K machine before big stop semantics. You said like it wasn't possible in small step and either impossible in big step.
There was some prior work on compiling to the K machine. It's actually in the PFPL textbook. The problem with that work, in some sense, is that it's not effectful and has no hope of being so, because the most it can reason about is terminating computations for the exact same reason that I brought up in the talk.
Let's thank the speaker again.